Fine. Let's start. Right now, as you sit here, the sun is shooting at you. Not occasionally. Not during solar storms. Always. A constant stream of charged particles, protons, electrons, helium nuclei, blasting outward from the sun at somewhere between 400 and 800 kilometers per second. That's over 1,000,000 miles per hour. Every second of every day, this invisible plasma wind is washing over the Earth at speeds that would reduce any spacecraft we've ever built to a memory. You don't feel it because Earth's magnetic field is silently, constantly deflecting it. That bubble of protection we live inside, the magnetosphere, exists specifically to stand between you and a 1,000,000-mile-per-hour particle stream. It's been doing this for billions of years without a thank you. And here's the thing that sits with me about this one. That 1,000,000 miles per hour is the baseline. The quiet Tuesday of space weather. When something unusual happens, it gets considerably worse. We'll get to that. The universe is not a peaceful place. It just looks that way from down here. Number 9, the Christmas Eve record. On December 24th, 2024, at 11:53 in the morning, UTC, NASA's Parker Solar Probe set a record that will likely stand for a very long time. It became the fastest human-made object in history. 430,000 miles per hour. 692,000 kilometers per hour. Washington, D.C. to Tokyo in under a minute. The engineers at Johns Hopkins Applied Physics Laboratory got a 2-day late Christmas present when a beacon tone confirmed the spacecraft had survived. Because at that distance from the sun, 6.1 million kilometers above the surface, survival is not a given. The heat shield was absorbing temperatures approaching 1,000 degrees Celsius. The spacecraft's interior stayed near room temperature, and it was moving faster than anything we have ever built. Here's the part that should recalibrate everything. 430,000 miles per hour is 0.064% of the speed of light. Not 6%, not 0.6%, 0.064. The fastest thing humanity has ever created is barely registering on the scale we're going to be talking about for the rest of this video. One more detail worth knowing. Parker didn't just point itself at the sun and accelerate. To fall that close to the sun, it actually had to slow down relative to Earth's orbital speed. Otherwise, it would just keep orbiting too far out. So it used Venus as a brake, 7 times. Over 6 years. The fastest human-made object in history needed to use a planet as a speed bump to reach its destination. The universe has a sense of irony. Number 8, the cannonball pulsar. In 2017, a group of volunteers contributed their spare computer processing power to a project called Einstein at Home, a distributed computing network that combs through data from NASA's Fermi Gamma Ray Space Telescope, looking for things professional systems might miss. One of those volunteers found a pulsar, not just any pulsar, a dead star called PSRJ 0002+6216, which astronomers have, with characteristic restraint, nicknamed the cannonball pulsar. It is traveling at approximately 2.5 million miles per hour. It is dragging a tail of shocked particles and magnetic energy behind it that stretches 13 light years. And that tail is pointing, like an arrow, directly back to the supernova remnant that created it 10,000 years ago. The supernova exploded. The explosion sent a shockwave outward in all directions, expanding through space at tremendous speed. And the pulsar, the compressed, dead core the explosion left behind, outran it. The bullet left the gun, and then left the explosion too. It is now 53 light years from the center of its own birthplace. It could get from Earth to the moon in 6 minutes, a dead star, fired across the galaxy by a shockwave, and still going. A volunteer found this, sitting at home. It was hiding in data that professionals had already collected, and it took crowdsourced computing power from ordinary people to find it. There's something I find genuinely lovely about that, and then immediately unsettling, because the next question is, how many others are out there that nobody has looked at yet? Number 7. The star a supernova launched. US 708 was first spotted in 1982 by an astronomer named Peter Usher at Pennsylvania State University. It looked like a faint blue object in the outer halo of the Milky Way. Nothing special. No follow-up observations were published. It sat in the catalog, unremarked on, for over 2 decades. Then, in 2005, it got a second look. And then, in 2015, a team led by Stefan Geyer at the European Southern Observatory figured out what it actually was. A white dwarf, the cooling remnant of a dead star, traveling at approximately 1,200 kilometers per second, 2.7 million miles per hour. Fast enough to permanently escape the Milky Way's gravity. It is already leaving. It will not come back. What makes US 708 different from other fast-moving stars is its origin story. Most hypervelocity stars are flung out by the supermassive black hole at the galactic center, a gravitational slingshot near Sagittarius A. Not this one. The team traced its trajectory and ruled that out completely. US 708 came from somewhere else. It was once part of a binary system. 2 stars orbiting each other in a tight, compact dance. At some point, one of them, the more massive one, began pulling matter from its companion, accumulating it until it hit a critical threshold and detonated in what's called a Type 1, A supernova. The explosion vaporized it. The shockwave hit the companion star and launched it outward at 2.7 million miles per hour. Eugene Magnier at the University of Hawaii, one of the co-authors, put it simply, at that speed, you could travel from Earth to the Moon in 5 minutes. US 708 has been traveling for millions of years. Its partner is gone. It is heading into intergalactic space, the vast, cold, almost entirely empty void between galaxies. It will orbit nothing. It will encounter nothing. It will simply cool, very slowly, over billions of years, somewhere in the dark. There is something about that image I can't entirely shake. A star that survived the death of everything it was part of, now moving through a universe with no destination. Number 6. The near miss of July 2012. On July 23, 2012, an enormous coronal mass ejection, a billion-ton cloud of magnetized plasma, blasted away from the sun at between 2,500 and 3,000 kilometers per second, 4 times faster than a typical ejection. It tore through space, across the inner solar system, and directly through Earth's orbital path. Earth wasn't there. We were 9 days ahead of that position in our orbit. 9 days. The cloud passed through empty space, where Earth had been, and where Earth would be again. Instead of hitting us, it hit one of NASA's stereo spacecraft, a solar observatory almost perfectly positioned to absorb the full force of the event and measure it in extraordinary detail. Daniel Baker at the University of Colorado led the analysis, published in December 2013. His conclusion: if this CME had struck Earth, it would have produced a geomagnetic storm registering a DST index of negative 1,200 nanoteslas. The 1989 Quebec blackout, which knocked out power for 9 million people and lasted 12 hours, registered around negative 589. The Carrington event of 1859, the most severe geomagnetic storm in recorded history, is estimated at around negative 800 to negative 1,000. This one would have been worse. The irony, if you can call it that, is that because it hit a solar observatory instead of us, scientists have more precise data on this near miss than they have on virtually any actual disaster in history. The stereo spacecraft measured the magnetic field, the plasma density, the particle energies, all of it. Baker's team could model exactly what Earth would have experienced. Widespread power grid failure, most satellites disabled, GPS and radio communications gone, recovery time estimated at months to years. Some estimates put the economic damage at $2 trillion in 2012. And the reason we survived it is that our planet happened to be 9 days further along its orbit. That's not a safety system. That's luck. A 3,000 kilometer per second plasma cloud missed us by 9 days of orbital movement. And the only reason we know how close it was is that something was watching when it happened. Number 5. The black hole that got kicked out of its own galaxy. In 2023, Yale astronomer Peter Van Dockum was examining archival images from the Hubble Space Telescope when he noticed something strange. A thin, faint line in one of the images, stretching away from the center of a distant galaxy. Not a streak from a passing satellite. Not an instrument artifact. Something else. He looked closer. The line was 200,000 light years long. Twice the diameter of the Milky Way. And it appeared to be made of newly formed stars. Stars that shouldn't exist in that location, strung along this narrow corridor like lights on a wire. His interpretation? A supermassive black hole had been ejected from that galaxy, kicked out by the gravitational recoil of a black hole merger, and was now plowing through intergalactic space at approximately 954 kilometers per second. 2.2 million miles per hour. As it moved, it was compressing the gas ahead of it, triggering new star formation in its wake. The trail of newborn stars was the proof of its passage. In December 2025, Van Dockum's team published new observations from the James Webb Space Telescope confirming the structure. The bow shock at the front, the compressed gas being pushed ahead of something massive moving very fast, was visible. The black hole, now designated RBH1, has a mass estimated at somewhere between 10 and 20 million times the mass of the Sun. It is invisible. Black holes are. You cannot point a telescope at RBH1 and see it. You can only see what it does. The stars it births as it moves. The gas it compresses. The scar it leaves across 200,000 light years of space. Something with the mass of 20 million suns is racing through intergalactic space right now, and the only evidence of its existence is a trail of stars it accidentally created, an invisible object leaving visible footprints. Number 4. The star orbiting our own black hole at 8% light speed. At the center of the Milky Way, 4 million solar masses are packed into a region roughly the size of our solar system. We call it Sagittarius A star, and crowded around it, in a dense cluster called the S cluster, are dozens of stars doing something they absolutely should not be doing: surviving. In 2020, astronomer Florian Peisker and his colleagues published observations of a star designated S4714. It orbits Sagittarius A star once every 12 years on an orbit so elliptical it's almost parabolic. An eccentricity of 0.985. At its farthest point, it's manageable. At its closest, it comes within about 1.9 billion kilometers of the black hole. For context, that's closer than Uranus is to our Sun. At that point, S4714 is moving at approximately 24,000 kilometers per second. 8% of the speed of light. A star, not a particle, a star, moving at 8% of light speed. At that velocity, it would cross the continental United States in roughly 1/5 of a second. The Parker Solar Probe, which we celebrated a few minutes ago for going 430,000 miles per hour, is moving at 0.064% of light speed. S4714, at closest approach, is moving at 8%. Those two numbers occupy completely different universes of scale. And here is the thing that genuinely bothers astronomers about this. S4714 shouldn't be there. Stars don't form in the intense gravitational environment that close to Sagittarius A star. The tidal forces would tear apart any gas cloud trying to collapse into a star long before it got started. So S4714 must have formed somewhere safer and then migrated inward over time, pulled into a tighter and tighter orbit through gravitational interactions with other stars in the cluster. It has been falling inward, slowly, for who knows how long. And every 12 years, it makes its closest pass at 8% light speed, and then swings back out. And nobody really knows how much longer it can survive doing this before something in that environment finally ends it. It is worth mentioning, in passing, that jets of plasma fired out along the axis of active black holes have been observed moving at 99.9% of the speed of light. Solar system-sized blobs of matter. At that speed, they appear from Earth to be moving faster than light, a genuine geometric illusion that was predicted theoretically before anyone ever saw it. Not a violation of physics, just physics being stranger than intuition allows. Even compared to that, S4714 is not the fastest thing at the galactic center. It's just the fastest intact star. Number 3, the Amaterasu particle, May 27th, 2021. A single subatomic particle entered Earth's atmosphere over the Utah desert and triggered a cascade of secondary particles that spread across 48 square kilometers, setting off 23 detectors in the telescope array experiment. 507 surface detector stations covering 700 square kilometers outside Delta, Utah. Professor Toshihiro Fuji at Osaka Metropolitan University looked at the data and thought there had been a mistake. The energy reading was 244 exaelectron volts. That's roughly 40 million times more energy than the most powerful particle accelerator ever built. The Large Hadron Collider can produce in a single collision, in a single particle. He checked again. It wasn't a mistake. They named it the Amaterasu particle, after the Shinto sun goddess. And then they asked where it came from. Cosmic rays this energetic are rare, but they're not entirely unprecedented. The Oh My God particle in 1991 held the record before this one. Both detections happened in Utah, which is less cosmic conspiracy and more a practical result of Utah having flat terrain and dark skies ideal for these detectors. The physics requires that particles at this energy level can't travel enormous distances without losing energy through collisions with the cosmic microwave background radiation. So the source has to be relatively nearby, in cosmic terms. Nearby, meaning within a few hundred million light years. They traced the trajectory back, and the direction it came from pointed toward the local void. A region of space that is, for practical purposes, empty. No galaxy with the kind of extreme environment needed to accelerate a particle to this energy. No black hole, no active galactic nucleus, nothing on the map that explains it. Professor John Bells at the University of Utah, speaking in a published context about ultra-high energy cosmic rays more broadly, offered a list of possible explanations. On that list, defects in the structure of spacetime, colliding cosmic strings. He prefaced it with, "I'm just spitballing crazy ideas that people are coming up with because there's not a conventional explanation." A 2026 study from the Max Planck Institute suggested the Amaterasu particle may have originated from M82, the Cigar Galaxy, a known starburst galaxy, after the particle's path was bent by magnetic fields in the Milky Way in ways the original trajectory reconstruction hadn't fully accounted for. That's a more conventional explanation. It might be right, but here's the thing. The Oh My God particle, which we detected in 1991, has a similar problem. Decades later, its origin is still unknown. The source of both particles, the two most energetic cosmic rays ever detected, points to nothing we can identify as capable of producing them. That's not a solved mystery with a tidy answer. That's 2 data points and an open question. Something out there is firing particles at us at speeds we can barely write down. We don't know what it is, and it's been doing it for at least 30 years. Number 2, the Oh My God particle. October 15th, 1991. Utah. A detector array called the Fly's Eye. A set of mirrors designed to catch the faint fluorescent glow that high-energy cosmic rays produce as they streak through the atmosphere. Recorded something it had never seen before. The team was led by Dr. Eugene Lowe at the University of Utah. A researcher was on shift in what was described as an old, rat-infested trailer parked on top of a desert mountain. The particle that hit the atmosphere that night was almost certainly a proton. A single proton, one of the basic building blocks of matter, carrying roughly the same mass as a hydrogen atom's nucleus. It was moving at 0.999999999999999999999999999999999 times the speed of light. Let's think about what that number actually means. If you lined up a photon, a massless particle of light, the fastest thing in the universe, and this proton at one end of the observable universe, and let them race to the other end, the photon would win. The photon's lead across a distance of 93 billion light years would be less than a centimeter. The particle carried 320 exa-electron volts of energy. One proton with the kinetic energy of a baseball traveling at 90 kilometers per hour. Not a large number in everyday terms. The reason it's staggering is that it's concentrated into a single subatomic particle. David Chieda, an astrophysicist at the University of Utah who has spent years studying this, put it like this. It's like you've got a gorilla in your backyard throwing bowling balls at you, but he's invisible. Now, here's where the physics starts to strain. There is a theoretical limit called the GZK cutoff, named after physicists Greisen, Zatsepin, and Kuzmin, who independently predicted it in 1966. It states that cosmic rays above a certain energy threshold should be absorbed over long distances by collisions with the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. Above that energy, a particle can't travel more than a few 100 million light years without losing most of its energy. The Oh My God particle was above that threshold, which means its source had to be relatively close. The team looked in the direction it came from. There was nothing there capable of producing it. No blazar, no active galaxy, no known astrophysical accelerator, just empty space, pointing back at the question. The Oh My God particle still does not have a confirmed source. After more than 30 years. The Amaterasu particle, which followed it, has a candidate now. But the Oh My God particle remains unexplained. Something accelerated a single proton to within a centimeter-length margin of light speed across the entire observable universe, and we have no idea what. That's not a comfortable sentence. It's just a true one. Number 1, you are already moving faster than light. You are moving faster than light right now. Not in a poetic sense, literally. From the perspective of certain galaxies, you, sitting wherever you are, not in a rocket, not in orbit, just existing on a planet, are receding from them faster than light can travel. Here's how. The universe is expanding. Not in the sense that galaxies are flying through space away from each other, in the sense that space itself is stretching. Every point in the universe is getting farther from every other point, not because things are moving through space, but because space is growing. The galaxies are mostly just sitting there. It's the distance between them that increases. Einstein's speed limit, the rule that nothing can exceed light speed, applies to motion through space. It says nothing about the expansion of space itself. General relativity, the same framework that gives us the speed limit, also predicts and permits the expansion. There is no contradiction. The universe is not breaking its own rules. The rules just turn out to have finer print than most people realize. The rate of expansion is described by the Hubble constant, approximately 70 kilometers per second per megaparsec. That means for every megaparsec of distance between two objects, roughly 3.26 million light years, those objects are separating at an additional 70 kilometers per second due to expansion alone. At a certain distance, that accumulated expansion exceeds the speed of light. That distance is called the Hubble sphere. It sits at roughly 13.77 billion light years from us. Any galaxy beyond that threshold is currently receding from us faster than light. And here's the part that stops most people. We can still see them. We can see galaxies that are right now moving away from us faster than light because the light they emitted billions of years ago, when they were closer, before they crossed the threshold, has had time to reach us. Any light they emit now toward us will never arrive. It's swimming against a current that keeps getting faster. Every galaxy above a redshift of 3, which astronomers have cataloged by the thousands, is receding from us superluminally, right now, as you watch this. And there is a cosmological event horizon, roughly 17 billion light years away. Any light emitted right now from beyond that boundary, moving toward us at the full speed of light, will never reach us. Not because it isn't trying, because space between here and there is expanding faster than the light can cross it. That horizon is not static. In a universe dominated by dark energy, it is, over vast timescales, effectively shrinking, meaning that over time, more and more of the universe passes permanently beyond what we can ever observe or know about. Right now, something is happening 17 billion light years away. Maybe something extraordinary. The light from it will never reach us. It might as well not exist from our perspective. And from their perspective, we crossed that same horizon long ago. From a certain cosmic point of view, every single one of us is already moving faster than light. We just call it Tuesday. That's the thing about space. You spend an hour talking about the fastest objects ever detected, particles that nearly keep pace with light, stars fired out of galaxies, black holes ripping invisible trails across 100,000 light years of space. And you end up here, sitting still, moving faster than any of it. Not through space, as space. Part of a universe that has been doing impossible things since before it had anything to do them with. The universe doesn't care about our speed limits. It wrote them, and it wrote the exceptions too. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.